Hello everyone, this is Nitin Satpute. Today's talk is basically about GPU for SNN, which is accelerating spike propagation for GPU-based spiking neural network simulations. This particular work has been submitted in Neural Networks Journal, and the link to the code and implementations are available, and the link has been provided. So the outline of this particular talk is basically introduction, where we will discuss about spikes, voltage and current, the basic modules regarding SNN spiking neural networks, and then the background and motivation, where we'll discuss the flow and the challenges, and later on the state-of-the-art implementations and what are the bottlenecks behind the SOTA techniques, and after that we will discuss the proposed approaches and finally conclude by providing the results and also some of the analysis which is really essential for this particular work. Introduction. So we'll go with this particular slide, which is spike. So the spike is nothing but whenever there is a change in threshold and that particular change in potential and the potential crosses certain threshold, there will be a spike, and this spike will be communicated to the neuron of the next layer. So if I say L and L plus 1, it means the neuron of the current layer, which is L, and the neuron of the next layer of the L plus 1. And also this information will be communicated in different time steps. But this spike will not only modify the current of the next neuron, but also the current of the present neuron, the current and potential of the present neuron. So the input to this spike is basically the potential. Whenever there is a change in potential and it crosses certain threshold, the spike will be communicated. The potential, as I said, whenever there is a change in potential, the spike will be communicated. So definitely it will be an instantaneous process, but the input to this potential will be from the same neuron at the previous time steps. So whenever there is a spike from the previous time steps or the potential change or the current, that will impact the potential of the current neuron at the same time step, at the current time steps, and this potential will be finally updated for the next time step t plus 1. For the current also, the inputs are basically current from the same neuron in the previous time step and also the spike from the previous time step, but also the input to this particular neuron will be taken from the previous neurons at the previous time steps if there is a spike from the previous neuron at the previous layer, which is L minus 1, and this particular current will modify the potential and the current of the same neuron in the next time steps. So the background and motivation, I'll be going through the flow. So if there is an input spike, which you can see, and this spike will communicate the information from one layer, the neuron of the one layer, to the another layer. So the current has been modified of the next neuron, and this current will impact the current of the same neuron at the next time step and also the potential. And finally, whenever there is a change in potential, the spike will be generated. So there is a spike in that particular time step, and then this particular spike will be communicated to the neuron of the next layer in the next time step, and also the potential and the current values of that particular neuron will be updated. So the process continues until all the iterations are performed or the required information has been generated, and finally it stops. Later on we'll be discussing about the state-of-the-art algorithms, which are N and Fs. So they are basically based on the number of neurons and number of synapses. The implementation is similar. It's only the number of threads we are launching. For N, we launched N number of threads. For S, we launched S number of threads, which is number of synapses, and for N, which is number of neurons. The idea is basically updating a potential and the propagating a spike. So how we can launch these two particular kernels? So in N and S implementation, the launching happens from the CPU side. So there are always intermediate communications. So that's a big bottleneck. So whenever we transfer our data and the SNN on a GPU, we have to launch the update kernel and spike kernel intermittently from the CPU side in each and every iteration. So that's a big challenge, big bottleneck, which we call it as a CPU bottleneck from N and S implementation. So next state-of-the-art implementation is active potential. So in the description about state-of-the-art implementations are given in the GitHub codes and GitHub repo. So this particular active potential implementation is basically the recursive implementation or the nested implementation. So whenever we launch a update kernel, this update kernel will propagate a spike, and the spike propagation will be launched as a child kernel on the GPU. But the big problem here is the number of child kernels which can be launched, and it has a limited depth, and there will be a lot of many communications in between the threads, which will be time consuming if the number of spikes increase drastically. So that's a big bottleneck. We cannot invoke a lot many child kernels if we have a lot of large number of spikes. So the proposed approaches are basically involved in order to reduce these challenges, these bottlenecks. So the active block approach, which is based on the number of computing blocks which are available on the GPU. So here we launch the number of active blocks, persistent computing blocks, and the spike kernel which was launched from the CPU side in NNS algorithm is being transferred to the GPU. So now this launching of a spike is happening on the GPU side, but we need an interblock GPU synchronization in order to validate the data in between different threads. So here the intermediate communications has been reduced by some percentage which were happening for launching a spiking kernel. So here the idea is we are trying to balance the workloads between CPU and GPU. But sometimes we don't want our CPU to be busy with this particular task. So CPU wants to do some different tasks. That's how we want to program it. And the GPU need to be allocated only for this particular strategy, for this particular application. So what we have to do, single kernel launch, which will launch a kernel on a GPU, and the final output will be collected and communicated to CPU. So you launch a kernel and the number of iterations will happen on a GPU side instead of CPU. So so here there will not be any interventions from the CPU. Launch SNN data and the kernel, and the computations and processing will happen on a GPU, and finally the last results, the final results will be communicated back to the CPU. So definitely the temporal evaluations we will not consider here, only the final output. But if you want to consider the temporal evaluation, we can proceed with the previous implementation, which is AB implementation. So this is the conclusion, the GPU for SNN, the codes, the state-of-the-art approaches, and also the proposed approaches are available on the GitHub. So where we get a lot of speed up, depending on the number of spikes, the neurons and the synapse. And here we implemented the SOTA and the proposed algorithms on the low end and the high end server GPUs. So the low end GPU is basically Quadro, and the high end basically Titan and Volta GPUs. We compared AB and SQL algorithms for low spiking, medium spiking, and densely spiking single layer SNN, and found out that the proposed approaches are quite efficient and faster on GPUs. So this is all. If you have any questions, please email me or let me know. Thank you.